Okay, this is lesson 4.1, Quadratic Relations. As I've mentioned now several times, a very, very important lesson because it forms the basis for the rest of your high school math career. Quadratic Relations. We have a whole course in this in grade 12 called Advanced Functions. Functions is another word for quadratic relations. Okay, so the definition of our relation is an identified pattern between two variables. So relation can be expressed in three different ways: numerically in like a table of values, graphically on a graph, and then algebraically as in an equation. Okay, most relations that you have studied in mathematics so far have been linear. Many nonlinear relations also exist in real life. So a linear relation is a relation between two variables that forms a straight line when graphed. So an example here, we have y equals 2x plus 1. Also, the formula that you guys all know and love, y equals mx plus b. Okay, that is our linear formula. Okay. Next, we have nonlinear relations. So a relation between two variables that does not form a straight line when graphed. So an example of that, Rudy, if you can tell me, you remember what the equation is for a quadratic based on the videos that we've watched now? Remember what it is? Yeah? Very, very good. Very good. You remember that, okay? That is huge, huge, and very important. If you can store that in your memory, it's going to be of value for years to come. Okay, that is your standard form. That is your standard quadratic formula. All right? Next, a independent variable is a relation. The variable that you need to know first is the independent variable. It's the value that determines the value of the dependent variable. On a coordinate grid, the values of the independent variable are on the horizontal axis. So, if we think in x and y, right? Here's my x, and here's my y. So my x is my independent, and my y is my dependent. Okay? Over here. Dependent variable in a relation is the variable whose value depends on the value of the other variable is the dependent variable. Sorry. The variable whose value depends on the value of the other variable is the dependent variable. Okay, so on a coordinate grid, the values of the dependent variable on the vertical axis, y. All right? So identify the independent and dependent variable in each relation. So it says the older John gets, the taller he is. Okay, so if we are measuring age and height, we're trying to determine which one would go on the x-axis and which one would go on the y-axis. Okay. In this case, age is independent. We know age is going to increase with time. So time is almost always the independent variable. And then in this case, we're measuring his height. So y is your height. So this is your measured variable. And your measured variable is always your dependent variable. And your age is your independent. And it's typically something that is given, right? It's something that changes the dependent variable. So as a plane descends, the more time that passes, the lower the plane's altitude. So as I mentioned, time is almost always the independent variable, right? Cannot change time, always moves on. We all get older, whether we like it or not. X and y, x is going to be equal to time. And then y, again, is going to be equal to height in this case. Okay? At a deli counter, the price of a customer's order is based on its weight. Here we go. We're at a deli counter. Okay? What would be independent and what would be dependent at a deli counter? Okay? The weight is going to be the independent variable. Even though the weight is calculated from a scale, in a way, it's really the cost that is calculated based on the weight. right? Like how much meat you're buying at the deli, okay? So the cost is the dependent variable, and the weight is the independent variable. Does that make sense? Okay, you might say, oh, well, weight is calculated. Well, not really. You're right. It's put on a scale and it's weighed, but it's actually the cost that's calculated based on that weight. Okay? Next, the more tickets I sell, the more money I have. So in this case here, the tickets would be the independent variable. Okay? You might say you can't control how many people are buying your tickets, but the earnings are what you are calculating based off ticket sales. That's how you know that the Y is the earnings, the dependent variable. Y is dependent. All right? Any questions so far? Next, line of best fit, or good fit. It's a straight line that comes closest to the points on a scatter plot. What is a scatter plot? Well, it's just a bunch of points on a grid. Okay, so what is the line of best fit? It's the line that goes through sort of the middle of all of these points. Okay? The curve of best fit is a curve that comes closest to the points on a scatter plot. So here's your scatter plot. Again, a bunch of points. You are trying to estimate a curve that goes through the middle of the majority of the points. All right? That's line of best fit and curve of best fit. Okay. Relation 1 and 2. The following data points follow linear relations. Draw lines of best fit for the data points. You ignore outliers when you do this process, and your line must be straight. Note, you are not connecting the dots like you did in kindergarten. So we're not connecting all these dots. We're actually taking a ruler, and it's already populated here for me, but not for you. You're going to create this line that goes, again, through the middle of all of those points. Likewise, you're going to do that over here. And you are eliminating these points here. This point, and this point, they get eliminated. Why? Because these are considered outliers. Okay, what is an outlier? An outlier is a point that does not follow the data set. Okay? You can't really make a curve of best fit that follows this point. You're not going to come down here and curve back up. You cannot do that. So these have to be ignored. Okay? Yep.
Why are outliers even on the graph?
Why what?
Why are outliers on the graph?
Good question. Very good question. Why do these points exist? Anybody have an answer for that? Why you think? It's good. Now it's gonna, Lucas. The answer is gonna. RC, what's your answer?
Is it like for statistics there are always like outlier statistics?
There are, yeah, but I think he's asking why. It would really come down to what we're actually measuring here. Okay. Okay. So you might say that. I just can't think of a better example, but you might say that like the heavier somebody is, the stronger they are. Okay, and you might take 30 people. You measure their weight, okay, and you measure their strength. Okay, so you're measuring the weight as the independent and their strength as the dependent. And you might determine that, hey, as these guys get heavier, they get stronger. So you might have a bunch of these dots that all go in a vertical line. Okay? Now you might have a person, however, who's very thin, but he's all muscle. Now all of a sudden, he doesn't weigh very much, so he's down here in weight, but he's very strong. He's up here in strength. He's an outlier. He's a statistical outlier. So depending on your particular example, you will have outliers. Okay? Another reason could be an error. It could be human mistake. Maybe you were measuring this guy's strength and you put in the wrong value. You were just like off by a number on your calculator. And so he's an outlier. So that outlier then gets ignored because there was a mistake there. A lot of the time, Lucas, it's human error. That's a mistake. But then you have these natural freaks, these genetic freaks, that they're outliers, right? Like pretty much everyone that plays in the NFL is likely to be an outlier. You got guys that weigh 300 pounds, but they have 6% body fat. That is not normal. It is a genetic outlier, okay, in that particular example. So any particular experiment, you're going to have these outliers. A lot of the time it's human error, but sometimes it's just the nature of the experiment or the measurements that you're taking. Does that answer your question, Lucas? Yeah, good. Okay, so relation 3. The following data points follow a nonlinear relation. So you're going to draw a curve of good fit for the data points. So that's this curve here. You are going to try and recreate this curve as best you can. Now there's not an exact curve that is right. Like I'm not saying mine has to be exactly right and yours is wrong, but you're going to try and fit right in the middle of those points. Again, you are ignoring this point, this point, this point, and even these 2 points are kind of, you're just splitting the difference, right? So these are ignored because they're outliers. All right, it says, draw a curve of good fit. Your curve must be smooth, not jagged, and you ignore any outliers in the process. It's not a V, it's more like a U. So this is a relation that's nonlinear. You need to draw the curve of best fit. It is quadratic, and you'll learn more about these in 4, 5, and 6, which we'll learn now. Any questions so far? All right, moving right along. Quadratic relations graphically. So not every nonlinear relation is a quadratic. Okay? The graph of a quadratic relation is called a parabola, and it is U-shaped and symmetrical. Identify the type of a relation that each graph below represents. Okay, so I don't know. Do you have on your notes these lines or not? You do? Yeah. Okay. So we are trying to identify the different types of lines here. So who can tell me? Let's just start over here. Douglas, what relation is this line here? It's going like this. Okay. Douglas is going to tell us this line. I'm going to draw an arrow here. And we're going to say that line is what type of relation?
Linear.
Linear, yeah. And we know it's linear because it's a straight line. We know the formula for this line would look something like y equals mx plus b. Okay, we actually know b would be right around 5 up here, 4.5, something like that. Okay. What kind of relation is this, Chenier? This one and this one. What kind of relation are these? This one and this one. Yes, quadratic, yes. Quadratic, or you could also say parabola. Either quadratic or parabola. Quadratic. All right. Now we have this wave here, and you guys don't know this, but this type of relation is called a sinusoidal curve. You'll learn that next year. Sinusoidal curve. So it's a repeating wave pattern. Okay, you might just call it a wave pattern as well for now. And then this curve here that comes up, comes down, comes up again. Not even sure what this one would be called. Let's go with question mark for now. I don't know that it has a set name, but it's definitely nonlinear. Let's call it nonlinear. How about that? Nonlinear, and we'll say it's non-quadratic as well. Okay, so it's different than either. 4. Handshake problem. Consider a group of people where everybody is to handshake everyone else's hand exactly once. Create a table of values that represents the number of handshakes versus group size. Plot the values and decide what type of relation it is. Okay, so let's see what's happening here. Here we have our group size. They handshake once. Here we have our group size of 3. This guy handshakes her. She handshakes her. She handshakes him. So we have all of these handshakes happening. Okay, so how do we do this? How can we cancel? Well, count them. So I have my graph here, and I have my handshakes down here. So let's look at the first one here. Well, when we have a group of 0, we know we have 0 handshakes. That's obvious. You have no one to handshake. When we have a group of 2 here, we know we have one handshake because they're going to just handshake each other and then it's a done deal. So we have a group size of, 1 is also 0 handshakes, 2 is 1 handshake. Okay? When we have a group size of 3, now we're going to have 3 handshakes happening. Okay, so 3, 3. When we have a group of 4, well, if we count all the handshakes here, we have 1, 2, 3, 4, 5, 6. So we have 6 handshakes. Okay? So we get this pattern forming here. 1, 3, 6, 10, 15. Anybody have an idea of what we're going to do next? What do you think? Milk it. Yup, you got it. We're going to get the first difference, and then what? We're going to get the second differences. Okay, now how do we get these differences? You just subtract one from the other, right? One down. It's the same exact way you did in grade 9 when you're doing the first differences, but you just do it twice. Second difference is now you're subtracting these. Okay? And wow, lo and behold, what do we find? We find out that our second differences are all the same. Therefore, what? RC. Second differences are all the same. Therefore, what?
Quadratic.
This is a quadratic. Anyone know what the last word I'm going to write is? Yes. Very good. Relation. Is that what you're going to say, Japhet? Very good. Quadratic relation. Yeah. Perfect. Okay. Since F are not, since the first differences, that's what this is. Triangle is also means differences. Okay. Another cool little symbol for you. Triangle means differences. So we have, since the first F differences are not constant, this is a non-linear relation. It's not a straight line. Not a straight line. Okay? Notice the second differences are constant. Therefore, this relation is quadratic. Okay? So as your number of people goes up, your number of handshakes goes up, and this is called exponentially. Why is it called exponentially? Because we got that square on top. That's an exponent. So this relation, this is an exponential increase, right? Our handshakes are going up a lot faster than the number of people. These are going up by 1. This is going up by 3, 4, 5. It's going up exponentially. Okay? Any questions there? That was example 4. Which page am I on? That was 3, 4. Is this the next page? No? This is, right? No.
Yeah, I'll take this. Next page.
I don't think I have that page. Let me see. Shoot, I don't have that page. Can I borrow somebody's? I'm gonna write it for you. Maybe. I don't know why I don't have that page. Is this it? Yeah, I don't have page 5 for whatever reason. That's really weird. All right. Okay, let's keep going. Example 5. Here we go. Determine whether each relation is linear, quadratic, or neither. Okay, so we're going to calculate the first difference here. So I do -1 minus -3. So it's actually -1 plus 3 is going to be 2. 1 minus 1, so it's 1 plus 1 is 2. 3 minus 1 is 2. 5 minus 3 is 2. Okay? So our first differences are the same. So we don't need to do the second difference because we know this relation is linear. Linear because first differences are the same. Next one, B. First differences, 1 minus 0 is 1. 8 minus 1 is 7. 27 minus 8 is 19. 64 minus 27 is 40, 30, 37? Yep. 7 minus 1 is 6. 19 minus 7 is 3 plus 9. It's not going to be the same.
It's neither, sir.
Yeah. So this is, sorry, why am I blanking here? 12. And then 37 minus 19 is 18. Yeah. Yeah.
Will we ever learn about third differences?
No. We won't. No. All right, keep going. This relation is neither linear nor quadratic. No, it's just neither. There's no word. Because first differences and second differences are not the same.
Mister,
Yeah.
can we just call it nonlinear or no?
No, because quadratics are nonlinear as well. So you can't just call it nonlinear. Okay, C. First differences. I'm assuming we're going to get a quadratic here eventually. 0 minus 6 is negative. Sorry, 0 minus 6 is negative 6. 12 minus 0 is 12. 42 minus 12 is 30. And 90 minus 42 is 48. Okay. 12 minus 6. So that's 12 plus 6 is 18. Here we go. 30 minus 12 is 18. And then 48 minus 30 is 18. So this relation is quadratic because second differences are equal. Next one, last one. 4 minus 3 is 1. 7 minus 4 is 3. 12 minus 7 is 5. And then 19 minus 12 is 7. Okay, now I minus these. I get 2, 2, and 2. And this is quadratic because second differences are equal. Any questions? Super easy, right? I hope. This is the next page, correct? Yes? Right, Jaden, next page, you with me?
Yeah.
All right, it says, read from the graph. We still got time, we can do this. Read from the graph, fill in the table, calculate the differences, and decide whether the relation is linear, quadratic, or neither. Super easy here. We're just going to look at the points. We're going to enter the y values from the point. So negative 1, 2. So I'm just looking at the x value. I'm going to the x value, finding the y value. So in this case, it's 2. Going to the x value, finding the y value on the parabola. In this case, it's negative 1. Going to the x value, 1. Finding the y value is negative 2 is here. Going to the x value, 2. Finding the y value is negative 1 here. Okay. Going to the x value, x. Finding the y value is up here is 2. Okay. That gives me my y values here. Then I calculate my first differences. So negative 1 minus 2 is going to be negative 3. Negative 2 minus 1 would be negative 1. Okay, because it's negative 2 plus 1 is negative 2. And you can use your calculator for this if you're not comfortable with the double negatives. But make sure you know how to use your calculator. We get these as the first differences. We then do the same thing and get our second differences. And what we find out here is that it is a quadratic. Why? Because the second differences are the same. So we know it's a quadratic relation. Next, example 7. It says determine the missing values in a table provided data is quadratic. So it's telling us the data is quadratic, and it's asking us to find these values now. All right? So we're kind of going backwards a little bit here. Okay? So we need to determine what are the values in the table provided when our second difference is. And what does it give you? Does it give you any of these values? Can I see what you guys have in your notes? Oh, I can check here. 1 second. I want to see what it gives you. It gives you this 4, and it gives you this -3. All right. So if we have this 4, we need to determine if we know the second differences are going to be the same, right? Because it's telling us the data is quadratic. So the big giveaway here, where you can start, is, I know this is going to look weird because I already have it populated, but you have to start here with the second differences. If it's telling us it's quadratic, I know that all of these values have to be equal. Does that make sense? Okay, so I can populate -3, -3, -3. Well, if I know that this is now -3 and I have a 4 here, then I can determine what do I have to have this number to be for this to be a -3. Okay, and you could do that algebraically. You could be like 4 minus x, right, is equal to -3. Okay, I'm trying to solve for the number that I need to minus. You could do it in your head, but you could also do it algebraically. So then I get minus x is equal to 4 moves over, -7, and then I get x is equal to 7. All right, you could have done it just in your head, but if you wanted to, you could have done it algebraically. Okay, so then I get 7 here. Well, then if I have 7 there, then I can work backwards again. And I say, what number needs to minus -6 to get 7? Well, it's 1. Okay, you can do it in your head. Or again, you could do x minus -6 is equal to 7. Here's the algebraic way to do it. So you have x plus 6 equals 7. X is equal to 1. Okay? Well, now that I have this, then I have my differences of 7. I can then work the exact same way and find out all of these other values. Okay? Working backwards from here, -3. What has to minus 4 to get -3? Well, it needs to be 1. Okay? Well, then if I have 1, I can work back this way to get my 5. So 5. So what minus 1 is 4? It's 5. Okay? Likewise, I start back here, -3. What has to subtract 1 to get to -3? Well, it's -2. And then what number here has to subtract 5 to give us 1? Well, it's 6. Okay? And you work backwards. Any questions with that one? Easy, easy. Next. Quadratic relations algebraically. Equations of linear relationships written in the form y equals mx plus b. Quadratic relations in the form y equals ax plus bx plus c. And now it says where a is not equal to 0. This is a condition. Why is that? Why is it saying where a is not equal to 0? Anybody know why? Yeah, Andrew.
Because if there's no x value?
If there's no x value?
Let's say if the line doesn't cross the x-axis.
No, not quite. What would happen, Andrew, if a was 0? What would happen to this?
Standard.
What?
It would be 0 times.
Yeah, and what would that give us? This whole thing would go away, right?
Yeah.
So you would just get y equals bx plus c. And that would be the same as this. So you can't have a equals 0. That's why they're telling you that. Otherwise, it won't be a quadratic. All right? That's why. Hope that makes sense. Is each linear equation quadratic or neither? Here we have a square. What is it, Shanir, when we have a square in the formula? What type of relation is it?
Square?
Yeah. When there's a square in the formula, what type of relation? What? Quadratic. Good. Josiah, what kind of relation is this? I got the answers here. Hold on.
Neither.
Neither. Good. And that's because it's a 7 here. Okay? So we have neither. Douglas, what type of relation is this?
Got it.
Very good. And that, oh no. Oh, trick. It tricked us both. The square is with the number, not with the x. Tricky. So they fooled us. So that's linear because this is just going to be a number, right? This will just be 25, negative 25. Lucas?
For the neither one, does it have to be a 2 for it to be quadratic?
This? Yes. The square has to be a 2. If it's a 3, neither. 4, neither. 10, neither. Has to be a 2. Okay, this one? Douglas? Linear, quadratic, or neither?
Quadratic?
Quadratic, yeah, and that's because there's a square on the x. You guys understand why this one was linear?
Yeah.
Because negative 5 squared is just negative 25, right? Yep.
So does the c in the next one, is it 7 squared? So it's y equals x squared.
This one?
Yeah, c. No. 7 squared.
This one?
Yeah. 3x squared is the c.
There is no, the c in this case is 0. So this is still a quadratic. If you just have this, that's still a quadratic, where just the c is 0. Okay? It's fine. The last one, quadratic, linear, or neither. Maxis. Quadratic, linear, or neither.
Linear?
Yep, linear. Very good, because it's just going to be 3x minus 7x is minus 4x, so it's linear. My goodness, still another page here. Looking for, this is what, 7? This one, right? This one?
Yeah.
All right. Okay, conclusion. We can judge if a relation is linear or quadratic or neither in 3 ways. Graphically, we just look at it. We do a scatter plot. Is the shape of the graph linear, parabola, or neither? Okay. We did that with this. Okay. Quadratic, linear, neither. Neither. Quadratic. Okay. Numerically, from a table of values using finite differences, are first differences the same? If they are, what does it mean? Yep, linear. Someone yelled it out. Are first differences not the same, but second differences are, Rudy? What is it if their second differences are the same? Rudy?
Yeah.
Second differences are the same. What does it mean? Quadratic. Yeah. Second, this is the whole lesson we've been talking about that, right? And then finally, if the first differences or the second differences are not the same, Adrian, it's going to be neither. Algebraically, from an equation, what does the algebraic expression of the relation look like? What is the degree of the expression? So this is a word that you have